Alrighty, so I want to start back at the beginning of class today. I know we kind of had to rush through it, but let's start here. What do we need to do when we're predicting products? Once we get our balanced equation, for single replacement before that, I suppose, but we need to decide, will it actually react? Will that reaction actually take place? Just because we can write it on paper doesn't mean it will necessarily happen. So we can see we're doing this primarily, well, not even primarily, only for the single replacement and double replacement reactions, right? Combustion reactions, try hard enough, it'll burn, and you're going to always get the same products, right? And with the composition or the synthesis and decomposition, those, again, you're not going to have to deal with this. So we're really focusing on single and double replacement. For single replacement, as we talked about in class, we're going to be looking at the activity series. I handed paper copies of these to you in class today, and this is really just shows relative reactivities of metals. We can also look at it for nonmetals, but for nonmetals, we really are limited to looking at the halogens, and you already know the trend in reactivity there, so you can follow that from your memory. For double replacement, we're over on the other side here, and we are looking at this thing called solubility rules. And basically, this is a list of rules that allow us to determine whether or not an ionic compound will be solid in water, or whether it will form an aqueous solution by dissolving in water. So moving forward, so these are the little notes on activity series. Again, we're just looking at reactivity, right? If we're comparing reactivities, the more reactive metal, right? The metals want to react by giving away their electron and becoming an ion. Nonmetals, they want to react by taking that electron and becoming an ion. So when we're trying to compare with this single replacement reaction, we're really looking at who's the most reactive element. When you're looking at the pure element, is it more or less reactive than the element it would be replacing that's in the compound, right? So if we're looking at our first example here, is potassium more or less reactive than calcium, right? If we look at our activity series, potassium is up here, calcium is down here, so potassium is more reactive, therefore it will kick calcium out, take its place, and become potassium chloride, giving you solid calcium metal. Let me get rid of that junk. So we looked at a few more examples. Down below that, if we look at zinc and magnesium, zinc is below magnesium on the activity series. Therefore, it is less reactive. So it is not able to shove its electrons back over to magnesium, is one other way to look at it. Therefore, it cannot replace magnesium. Magnesium is the more reactive metal. It gets to stay the ion, so nothing happens. And when you're writing this, when you're reporting this out, no reaction. That's exactly what I want you to say. It does not get to happen, okay? You can do the same stuff with the halogens. For example, if we have, chlorine with sodium bromide, right? Will that happen? Well, sodium is up here, chlorine is up there, bromine is below it, so chlorine is more reactive. Therefore, the chlorine can replace the bromine, so you would get sodium chloride and bromine. And again, we always have to balance, and there we go, we're happy, okay? So that's your single replacement. You're using the activity series. The more reactive element gets to be the ion. If there's no change in who is the ion, then there is no reaction, okay? In the first example here, we see there is a change in who is the ion. It was calcium, potassium was able to kick it out, so now potassium is the metal, there was a chemical reaction. Down here below, the magnesium is the more reactive metal. It is already the ion, so nothing is going to change, and we can see there is no reaction. Moving forward, we totally had to rush through the solubility rules. I'm so sorry. We ran so tight on time today. But I just want to kind of walk over it again. And really, you just have to practice. Like, you just have to start using these rules. And I want us to really start drawing these small particle models that you see here. We're going to focus a lot on that next class with our lab. We're going to be doing a lot of this, just really trying to see what is going on with these particles in solution. So like I was saying, we are using these solubility rules to determine if an ionic compound will dissolve in water or not, right? Is it going to be aqueous or is it going to be solid? And as this picture shows, right, because the silver chloride is a solid, right, and we know that, I'm just going to zoom up here really quick, we can see chlorides, right, salts of chloride are soluble. However, jump over to the exceptions and we see that silver is one of the exceptions. Therefore, silver chloride would be a solid compound. So we know that that silver chloride is going to be a solid. So in our picture here, we show the silver chloride down here together as a solid down at the bottom. Let's just look really quick. If silver chloride was aqueous, it wouldn't be down here. We would instead have our silver ion and let me get our chlorine ion, right? And they would still be chilling out in solution. And then notice we would have basically the identical, we didn't balance this equation. We'll do another one on the next page. I'll make an extra one for you to show it with balance. But you would see all the same ions would be in solution. So let's clean this up. We'll go to the next page. I'll use my solubility rules, you use yours, and we will look at just one more problem really quickly. So here we go. So let's see. I'm going to make it up as we go along. Let's wish me good luck. So let's say I have strontium nitrate. Okay, so strontium nitrate is SR is a 2+, nitrate is a 1-, so that's going to be SrNO3, 2, and that is an aqueous solution. Salts of nitrates are all going to be aqueous, so that's going to be aqueous. Let's add that to something else. Let's add that to sodium sulfate. Why not? NaSO4. Sodium is 1+, SO4 is a 2-, so we need an Na2. SO4, and that also is aqueous. So when I'm looking at my solubility rules, I see that salts of sulfates are aqueous, except if they are the strontium, the barium, or the lead. So I see the sodium sulfate is just fine, and it is in fact going to be aqueous. So when I'm moving forward with the double replacement, you really have to just go ahead and predict your products, right? Maybe skip balancing until you know if it'll work or not, but you do have to go ahead and predict your products. So you want to swap the partners. So you're going to have your sodium with your nitrate. Sodium is a +1, nitrate is a -1, so it'll just be NaNO3. And then let's not put a state symbol yet. We still need to figure that out. And then the other one would be strontium sulfate. And so tell me, okay, good, I didn't screw that up. So strontium, again, is a 2-, sulfate is also a 2-, so it'll be one of each for those as well. So SrSO4. Now we need to determine, and before I spend my time balancing, I'm going to make sure the reaction can actually happen, because why should I waste my time balancing if it's no reaction? If it's no reaction, I just get to say that. So I'm going to look at my rules here, and I'm identifying whether or not these compounds are going to be aqueous or solid. So I'm going to start here with my sodium nitrate, and I see at the very top of my solubility rules pretty much all salts of sodium are going to be aqueous. So I'm positive it's going to be aqueous. I'm just going to keep checking for your benefit, and I'm going to go down and see that, wait a minute, salts of nitrates are also all aqueous. So I am 100% sure this is going to be an aqueous compound, no doubt in my mind. Then I'm going to go and I'm going to look at the strontium sulfate, and I'm going to look for strontium, and I don't see it. And remember, as you look at those solubility rules, most of these are going to be listed based on the anion. So just kind of get used to looking for the anion. So I'm going to look up the sulfates. So SO4 2-, it's at the bottom of the first kind of chunk, looking at the soluble compounds. Salts of sulfates are soluble, but there's some exceptions. And one of the first exceptions is the strontium sulfate. So we have strontium sulfate here, so I know now that the strontium sulfate is in fact not going to be soluble. It is going to be a solid. It will form a precipitate. So if we put some drops of strontium nitrate in with some drops of some sodium sulfate, we would form solid strontium sulfate, and then there would also be that solution of the aqueous sodium nitrate. So let's balance this, and then I want to look at the small particle model, and then I'll call it quits. Let's see, I'm going to balance. I need a 2 here. That means I've got the 2 there, 1 there. I think that's balanced, right? We're good? Okay, so let's draw quick little beaker small particle models. So for these small particle models, a little slapdash, I apologize. I have to go cook dinner. But I want to just give each of my types of ions a symbol. And I have 4 colors here, so I'm going to make this really easy. You could do squares and triangles and diamonds and stars. You can do it however you want. It's just a lot easier when drawing these models to give a little symbol as opposed to having to write out the entire formula, right? So I'm going to say sodium is going to be green, and let's see, we'll make sulfate purple. All right, so my strontium ion is going to be red, my nitrate ions are going to be blue, my sodium ions are going to be green, and my sulfate ions are purple, I'm sorry. So one of the main purposes of, there's two main purposes for doing these small particle models. One is to really show, are we seeing a difference between before the reaction and after the reaction, right? Is there really a solid? Does that really make a change? The other thing is it's a really great way for me to be able to see, I don't know, on an assessment, whether or not you understand the difference between a subscript like this 3 here in the nitrate and a coefficient like this 2 over here in front of the sodium nitrate. So that's really a big part of what I'm wanting to look at here. So let's put everything that we have in the beaker before. And when I do this before beaker, this is everything is together, but nothing has happened yet. So consider this like time 0. So we have 1 strontium, we have 2 nitrates, we have 2 sodiums, and we have 1 sulfate, okay? Now, because it's a nice simple double replacement where they are truly just swapping and there is no disruption of my polyatomic ions, it is totally okay for me to just leave my polyatomic ions together and represent them as just one thing. I'm totally cool with that. There's other small particle modeling where we can rearrange it all and represent everything and all of that, but I find this really useful here. So then let's represent the other side. So my sodium nitrate is aqueous. So let's see, sodiums, again, I'm gonna have 2. I would hope that my numbers of things will balance out here. The nitrate is blue, and I'm gonna also have 2. The reason I have 2 of each of these, right, is again, because of this 2 coefficient here, right? The formula doesn't tell me I have that, but the coefficient does. Then over to my solid, since it's a solid, it's not up in solution, so I'm not going to put it in solution. I'm going to drop it at the bottom of the beaker. That's where a solid would go eventually, right? And so we've got our single strontium, and it is paired with that single sulfate, and they are together. They are connected, right? And they're at the bottom. They are not up in solution. We're going to do a lot of this small particle drawing as we move forward and we move through the lab to kind of represent these reactions. All right. So I am posting 2 separate worksheets on Canvas along with this. Be sure you do both of them. I'm also, I'm going to post the keys with them. I want you to be able to see what you're doing, make sure you're moving along correctly. They should work out just great. One of them is really just focusing on activity series. The other is just focusing on those solubility rules. Give it a shot, get through all of it. We'll be checking off homework next class just to keep that record for ourselves again. And then moving forward, I hope this is helpful. Again, sorry we had to rush through this in class today, but we'll get everything put together in the lab next class. It should be a fun lab. I think you guys will like it. All right, have a lovely evening and good luck.